Have you ever looked up at the stars and wondered if time passes the same way for everyone, everywhere? It's a question that has puzzled philosophers and scientists for centuries. We experience time as a constant, a river flowing steadily forward, carrying us all at the same pace. But what if I told you that river can speed up or slow down?
Ouch.
What if time itself is not the universal metronome we believe it to be?
Ouch.
This is the mind-bending reality uncovered by one of the greatest scientific minds in history. Albert Einstein's theory of relativity turned our understanding of the universe on its head. It revealed that space and time are not separate entities, but are woven together into a single fabric, space-time. And this fabric can be stretched and warped. This isn't just abstract theory, it has tangible, observable effects. One of the most fascinating consequences is a phenomenon called time dilation. It's the idea that time can pass at different rates for different observers. Why does this happen? The answer lies in two key factors: velocity and gravity. Let's start with velocity, or how fast you're moving. Imagine a thought experiment that has become a cornerstone of modern physics: the twin paradox. Picture two identical twins. Let's call them Anna and Ben. Anna decides to stay on Earth, living her life as usual. Ben, an aspiring astronaut, embarks on an incredible journey. He boards a futuristic spacecraft capable of traveling at a significant fraction of the speed of light, let's say 90% of it, heading towards a distant star system. From Anna's perspective on Earth, Ben's journey takes many years. She watches the calendars turn, celebrating birthdays and watching seasons change. To her, time flows normally, predictably. But for Ben, hurtling through the cosmos at near light speed, things are very different. According to Einstein's special theory of relativity, the faster you move through space, the slower you move through time relative to a stationary observer. Inside his ship, Ben's clock seems to tick perfectly normally. He eats his meals, performs his duties, and sleeps, all according to his own sense of time. He doesn't feel any slowing down. Years later, Ben turns his ship around and returns to Earth. When he lands, he's in for a shock. While he has aged only a few years during his voyage, decades have passed for his sister Anna on Earth. He steps out of his spacecraft, still relatively young, to find his twin sister, now an old woman. This is the twin paradox. From Ben's point of view, it was Earth that was moving away from him. So shouldn't Anna be the younger one? The paradox is resolved when we consider that Ben's journey was not symmetrical. He was the one who had to accelerate to near light speed, decelerate to turn around, and accelerate again to come home. This acceleration is what breaks the symmetry and makes him the one who experiences less time. It sounds like science fiction, but this isn't just a quirky thought experiment. It's a real, measurable effect. The fundamental principle is that the speed of light in a vacuum is constant for all observers, regardless of their own motion. To keep the speed of light constant for everyone, something else has to give. That something is time. As your velocity increases, your personal clock slows down from the perspective of a stationary observer to ensure that you both measure the speed of light as the exact same value. So what happens at the ultimate speed limit, the speed of light itself? If you could theoretically travel at the speed of light, time for you, relative to everyone else, would stop completely. You would traverse the entire universe from one end to the other, in what would feel to you like an instant, while billions of years would pass for the rest of the cosmos. Of course, anything with mass cannot reach the speed of light, as it would require an infinite amount of energy. But photons, the particles of light, have no mass. They are born and travel at this cosmic speed limit, and from their perspective, no time passes at all between their creation and their absorption. This velocity-based time dilation isn't just theoretical, it is practical applications we use every single day. Take the Global Positioning System, or GPS. Your smartphone or car's navigation system relies on a network of satellites orbiting Earth. These satellites are moving very fast, about 14,000 kilometers per hour. While this is nowhere near the speed of light, it's fast enough for special relativity to have a measurable effect. Their internal clocks tick just slightly slower than clocks on the ground. If we didn't account for this, the errors would add up quickly. Your GPS would become inaccurate by several kilometers every single day, rendering it completely useless. But there's another piece to the puzzle. Einstein's general theory of relativity introduced the second factor that affects time: gravity. The theory describes gravity not as a force, but as a curvature of space-time caused by mass and energy. Imagine space-time as a stretched-out rubber sheet.
Oh.
A massive object, like a planet or a star, creates a dip or a well in this sheet. The more massive the object, the deeper the well, the stronger its gravitational pull. Time is also affected by this curvature. The stronger the gravity, the more space-time is warped, and the slower time passes. Think of it as trying to roll a ball near the deep well. Its path is altered, and it takes longer to get across. Clocks in a stronger gravitational field will tick more slowly than clocks in a weaker one. This means time literally runs faster at the top of a skyscraper than it does on the ground floor, because the ground floor is closer to the center of Earth's mass and experiences slightly stronger gravity. The effect is minuscule, far too small for us to notice in our daily lives. But with atomic clocks precise enough to measure billionths of a second, scientists have confirmed this gravitational time dilation. They've placed one clock at sea level and another on a mountain and measured the difference. Let's go back to our GPS satellites. They're orbiting high above Earth, where gravity is weaker than it is on the surface. According to general relativity, this means their clocks should tick faster than ours. So we have two competing effects. The satellite's high speed makes their clocks slow down special relativity, while their higher altitude and weaker gravity makes their clocks speed up general relativity. It turns out the effect of gravity is stronger. When engineers designed the GPS system, they had to program the satellites to account for both of these relativistic effects. The onboard clocks are deliberately calibrated to run slightly slower to compensate for the net effect, ensuring they stay synchronized with clocks on Earth. Without Einstein's theories, our modern navigation systems simply wouldn't work. Time dilation is not just a concept for physicists to debate. It's a part of the technology that guides us through our world. So time is not the constant universal river we perceive it to be. It is relative, flexible, and tied to your motion through space and your position within a gravitational field. Every time you climb a flight of stairs, you are aging infinitesimally faster than someone on the floor below. The universe is a far stranger and more wonderful place than our everyday intuition suggests. The simple act of moving changes your personal experience of the fourth dimension. The faster you go, the more you travel into the future of the stationary world. It challenges our very definition of now. If time passes differently for everyone, can we truly say that events are happening simultaneously across the universe? Einstein showed us that simultaneity is also relative. This cosmic dance of space and time shapes everything, from the orbit of planets to the light reaching us from distant galaxies. It's a fundamental property of the reality we inhabit. So the next time you look at your watch, remember that the time it shows is personal to you. It's your unique path through the four-dimensional fabric of space-time. Understanding these concepts deepens our appreciation for the intricate and elegant laws that govern our universe. If you found this journey through time and space as fascinating as I do, consider exploring more with us. Be sure to subscribe to Space Repo for more deep dives into the mysteries of the cosmos. Thanks for watching.